Hi everyone. Today we'll take a look at DeMoivre's theorem. So I'm going to bifurcate DeMoivre's theorem into two parts. First is case 1. And case 1 says is basically if if n, right, the variable n is any integer then, right, then I'm going to write a simple statement here, right? So I'll change the color. I'll put it in yellow, or I'll keep it in maybe light blue. So, right, then the first is cosine of theta plus I sine theta raised to the power n is basically cosine of n theta plus I of sine n theta. Okay, and let me just show how, this basically comes, right? So I'll change the color again. So now I can write cosine of theta plus I sine of theta as e raised to the power I theta, right? I can do that. And from the previous video, if you've watched it or if you have learned in class, you would know that, right? And then I'm raised to the power n, right? Now, I apply the same thing, right? I apply my exponent rules. So when I apply my exponent rules, I get e raised to the power I n theta, right? And then this can be simplified as cosine of n theta plus I of sine n theta, right? And that's exactly what I get. So now, if I have to, sort of generalize this with r e raised to the power I sine theta, what I actually get is basically z is equal to, z is our complex number, r cosine of theta plus I sine theta, right? I get this, and if I, raise this to power some power, raise it to some power, what I get is r n raised to the power cosine, or let me do it, let me do it in a step later. I won't skip steps here. What I'll do is I'll write it like this. So r of cosine of theta plus I of sine theta. And then I'm going to keep another curly bracket over around. And I'm going to raise to the power n. Now, if I simplify this, what I'm left with is r raised to the power n cosine of n theta plus I of sine n theta. That's what it is. Right? Now, the second part of case 1, right? I'm going to use the same color that I did. I'm going to use light blue. So I'm going to have this, and I'm going to write right here is when, if I have cosine of theta 1 plus I sine theta 1 times cosine of theta 2 plus I sine theta 2. And I'm going to multiply this n times, right? So if I'm going to multiply this n times, I'm going to get cosine of theta n plus I sine theta n, right? When I do this, what I'm actually doing is I can, simplify this, or I can condense it. I can write this as cosine of theta 1 plus theta 2 plus theta 3 all the way up to theta n plus I sine, and I'm going to write the same thing in the argument section, right? Theta 1 plus theta 2 plus theta 3 all the way up to theta n. And now if you want me to prove it, I can, do it very easily. So I'll use the same colors like I did before. So I can write each of them as in Euler's form, right? So this would be, if I put an arrow down here, this would be e raised to the power I theta 1 times e raised to the power I theta 2, and so on and so forth until e raised to the power I of theta n, right? Now, again, when we're multiplying exponents with the same base, all we do is basically we just have to add these terms together, right? So what I'm left with is e raised to the power I, and factor it out, theta 1 plus theta 2 all the way up to theta n, right? Again, now if we expand this, this is the angle that's right here, this is the angle that's here. So at the end of the day, we're getting the same thing, right? Now let's look at one more small part, or I should say case 2, right? So let me change the color again. I'll take it purple, and I'll write it on the next page. So right here. So now let's look at case 2. So case two is the more important one, right? And basically, now case two, we're going to deal with square roots, right? That's where polar form and Euler's form comes in very handy, because it's really difficult to find the square root of some random complex number in its Cartesian form, or maybe square root may be possible because you can do z squared is equal to x plus iy, and then evaluate this, like we've done before as well. I've explained that before in my previous videos, so that can be a little easy. But what if you have z raised to power 1 by 7? Now what do you do here? Now you're gonna have to basically do x plus iy. So maybe let me, instead of writing x plus I, let me just write it as 1 plus I. I don't know. So 1 plus I raised to the power 1 by 7. Now, how would you, evaluate this basically? So actually, there would be something like this. So z is equal to 1 plus I raised to the power 1 by 7, right? So now the only way, you could do it, and if it's Cartesian, you could do z to the power 7 is 1 plus I, right? Like this. Then you would do what? X plus iy. You generalize it, raise to the power 7, 1 plus I. Then what do? You have to evaluate this. You can write x plus 7 plus blah, 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 blah. And all the way, and then you would have 1 plus I. Then you'd compare the real parts with each other, the imaginary parts with each other. And then, you probably get some simultaneous equation which you're going to have to solve. And I don't even think it's going to be a really, really complicated simultaneous. Like, it'll take decades for you to solve this question. So now that's where polar form and Euler's form comes in really handy, especially with DeMoivre's theorem. So what DeMoivre's theorem says, right? Let me erase all this unnecessary thing. I'm going to write what is important here. So let me erase it. So now DeMoivre's theorem says basically if you have a complex number in polar form or in Euler form. Let me write in polar form first. So if we have z is equal to cosine of theta plus I sine of theta, or let me write it like this: r raised to power 1 by n, right? So let me read this again: 1 by n, right? So the way we can find the roots is basically, well, we take out the modulus like this, but then we do is cosine of theta plus 2k pi upon n plus I sine of theta plus 2k pi all upon n. And I'm going to put this in square brackets just to differentiate it, right? Now, let me just tell you what are things here. So n is obviously, what root it is, basically the square root, the cube root, right? So n is basically, I would say, all positive and all integers, all integers, right? N belongs to all integers. And k is basically n minus 1. That's what k is, okay? So essentially, whenever you have to find the square root of a complex number, what you do is if you're given the complex number in the Cartesian form, you first convert it to polar form or Euler form, whatever you like, and then you apply this thing. So now, if I have to write the same thing for uh, Euler's form, what it would be is it would be something like this. So if z is equal to r e raised to power I theta raised to power 1 by n. If we evaluate it, what do we have? We have a very similar thing, right? E raised to the power I theta plus 2k pi upon n. And it follows the same idea, right? That k is less than n. K is one number less than n. And it basically, uh, yeah, so but that's what I mean. So let me just read out this again. 1 by n, right? So now let's look at a few simple questions first. What we'll do is we'll look at a few simple questions of uh, this one, and then we'll look at more of the roots of complex numbers. So we have our first question, which says use DeMoivre's theorem to calculate this expression right here. Now again, like I said before, we're given in Cartesian and we have it raised to some power n, right? So obviously we can, you know, expand it using binomial theorem. No issues with that. It's just that it'll take forever. So what we do is we convert it to polar or Euler form, and then we convert it back to Cartesian form because we were given this question in Cartesian, so we're gonna give the final answer in Cartesian. So now, how do we start? Obviously, we're gonna forget the power, right? Let's just look at 2 minus I times 2 root 3. Okay. How do we convert this to polar form? So obviously we need the modulus, right? So modulus of z is what here? It's 2 squared plus 2 root 3 whole square. So modulus of z is 4 plus 4 times 3, which is 12. And that is 16, so modulus of z is 4. That we have. Now we have to find the argument. So if we look really closely, right? 2 minus 2 root 3. So we're going to have this complex number in the fourth quadrant, right? We're going to have this number in the fourth quadrant. So maybe like 2 and then so 2 again and then 2 root 3, just like 1.7 times 2, just like 3.4. So 3.4 would be maybe somewhere right around here. So now if I draw my complex number right here. So this is 2, this is 2 root 3. So I know my theta is going to be negative because it's in the fourth quadrant, and because my theta has to be from minus pi to 2 pi, right? Sorry, minus pi to pi, not 2 pi. So it'll be 10. So basically I could get 10 inverse of 2 root 3 upon 2, which gives me pi by 3. But I know it's in the fourth quadrant, so I'm going clockwise, so it has to be minus pi by 3, right? Again, this all depends on how strong your trigonometry is and how quickly you can grasp finding arguments. I'm not going to explain, again, how I did this in detail because I've done in my previous videos. So I have my angle right here as well. So I can, condense this. I can write this as basically, so I'll take a new color. So I'll take the color and I'll take orange, and I'll write 2 minus, I always forget the iota. So 2 minus I 2 root 3 can be written as 4e raised to the power I minus pi by 3. Okay? And now I'm going to raise it to the power 5, which was already there. So now if I simplify this, what I have is 4 raised to the power 5 e raised to the power I can multiply this now, right? So I'll have minus 5 pi by 3. Right? That's what I'm going to have. So 4 raised to the power 5. Obviously, let's do this really quickly. 4 times 4 times 4 times 4 times 4. So this is 16. This is 16. And so I have 16 times 16 times 4. So 16 times 16 is 256. And times 4. And 256 times 4, which is 1,224. Okay, so that's this part right here. So 1024. Now this part, right? So this part is basically minus 5 pi by 3. Right now I can change this. I can change this really, nicely if I just add 2 pi, right? Because even if I add 2 pi, subtract 2 pi, the angle is always going to remain the same. So now if I add 2 pi now, what I'm going to have is 6 pi by 3. And if I do 6 pi minus 5 pi plus 6 pi, which is pi by 3. So I can write this as e raised to the power I pi by 3. Right, now I've simplified it to this. But now remember, we want the answer in Cartesian form again. So how I'm going to evaluate this again. How am I going to do that? I'm going to convert Euler's form to polar form. So I'm going to have 1024. I'm going to write this as cosine of pi by 3 plus I sine pi by 3. Okay. Now, when I do this, I know cosine of pi by 3 is half, right? So cosine of pi by 3 is half. So 1024 times half plus I of the square root of 3 by 2, because that's what sine pi by 3 is. So I have that. Now I just have to evaluate this. I'm going to have 512 plus I times 512, and that is my final answer. So at the end of the day, I used the properties, right? I used my properties of exponent, right? There was not really nothing new in this part. All I had to do was use my properties of exponent, know that, the first part of DeMoivre's theorem, which basically said when you have some, complex number raised to power n, you can just put that in the argument every time, right? And that's only possible when you convert it to polar form or Euler form. They can be interchanged, right? So obviously I converted it to polar form. I could have done polar form here. I didn't have to put it in Euler form, but I just did it because it's just I just have to write less, right? When I write less, I save time, and that helps me finish my exam much earlier. right? That was the reason why I did this. Now, when you have to evaluate it back to a Cartesian, you do need to convert it to polar, right? So from Euler, I went to polar just by, putting in theta, and then I evaluated accordingly. Let's look at a few more examples. All right, so in this question, we're given two complex numbers in polar forms, and we're asked to find z1 raised to the power 3, and upon z2 raised to the power 5. Okay, so let's break it up first. Let's find z1 raised to the power 3, so z1 cubed, basically, right? So I'll just draw a small line here, like this, and like this. So let me redo it again. So I'll draw one like this, and I'll draw one like this. Okay, so z1 is square root of 2 cosine of pi by 3 minus I cosine of 5 pi by 6. Now remember, we cannot directly apply DeMoivre's theorem here, right? Because we need it in the form cosine of theta plus I sine theta or minus I sine theta. That's okay. Whether we have plus or minus doesn't matter. If it's a minus, it's a conjugate. If it's a plus, it's just a normal complex number, right? We can assume it that way, right? So now let's try converting this into cosine of theta plus I sine theta, right? And the only way we can do this is basically we need this cosine to become a sine, and the only way we can do that is by basically doing basically. Wait, actually, let me restart again. So if we want to convert cosine of theta to sine theta, what we have to do is we have to do sine pi by 2 minus theta. So that's what we're gonna do here. We're gonna write cosine of 5 pi by 6 is equal to sine of pi by 2, right? So I'm going to write pi by 2 as 3 pi by 6, okay? Minus 5 pi by 6. So what I'm going to have, 3 pi minus 5 pi, 3 pi minus 5 pi, which is minus 2 pi. So minus 2 pi upon 6 is minus pi by 3. So I'd have sine minus pi by 3. So now if I put it back, so I'm going to have z times square root of 2 cosine of pi by 3 minus I sine minus pi by 3. So now if you remember, sine of minus theta is equal to minus sine theta. So if I take out the minus sign here, I can add a plus here, right? Basically a minus times a negative, which is a plus. So let me carefully add a plus here. And now we have our form cosine of theta plus I sine of theta, right? So now I can write this, or I can use applied DeMoivre's theorem here. So I want z cubed. It would be 2 root 2 because square root of 2 cubed times cosine of theta, which is um, cosine of pi plus I sine pi. Okay, I'm going to convert this into Euler form just so it's much easier to see, right? So I'm going to have square root of 2 e raised to power I pi. And I can write this as minus 1 if I want, but I'm going to keep it as it is because I want the final answer to be in polar form only, or polar or Euler forms, one form or the other. So I'm going to keep it here, and I'm going to just make a box around it so I know that's the answer for the first half. So let me change the color again. Now let's find z2 raised to power 5. So I know z2 is 2 times sine of 5 pi by 6 minus I sine pi by 3. Right? Now, again, I want cosine of theta plus I sine of theta or minus sine of theta. Even if the minus exists, it's okay. I can still work with it because I just know it's a conjugate, right? Okay, one more thing. If you ever come across a question, maybe they say Z star, just know that it's a conjugate. I didn't mention that anywhere, so I'm just going to mention it here. So I'm going to write conjugate. If you ever come across them in textbooks or something, just be aware. It shouldn't be a surprise to you when you see it. Okay, now let's continue, shall we? Great. So we have sine pi by 6, sine 5 pi by 6 minus sine pi by 3. So again, sine of theta is equal to cosine of pi by 2 minus theta. Okay, you have this. Now, how would we convert this? So we have sine 5 pi by 6 is equal to cosine of pi by 2. So I'll write it 3 pi by 2, 3 pi by 6 minus 5 pi by 6. Again, it would be cosine of minus pi by 3. So I have now, what I have here is, let me just rewrite it here again. So I would have 2 times cosine of minus pi by 3 plus, sorry, it was a minus. So minus I sine pi by 3. Okay, I have this. So my z sub 2 is 2. Now, how do I, write this in a form that, fits the general formula, right? So I know cosine of theta plus I sine theta. So this is minus theta. If this is theta, this is minus theta. If this is theta, this is minus theta. But I know that sine of theta is equal, sine of minus theta is equal to minus sine theta. So what I can do is I can actually put this minus sign back inside. So what I'm going to do is I'm going to write cosine of minus pi by 3 plus I sine minus pi by 3, like this. So now I have the same angle in both cases. Now I can convert this uh, into Euler form. So I'm going to have 2e raised to the power I minus pi by 3. And now I know z sub 2 raised to the power 5 will give me 32 e raised to the power I minus 5 pi by 3, like this. Now I'll put this in square brackets as well. Now all I have to do is I just have to evaluate this, right? So I'm gonna change the color again. So I'll write z1 cube upon z2 to the power 5 is square root of 2 upon 2 upon square 2 root 2 upon 32, and I'll have e raised to the power I pi upon e raised to the power minus 5 pi by 3. So now if I simplify this, I'll have square root of 2 upon 16 e raised to the power I pi plus 5 pi by 3. So I have 3 pi plus 5 pi, which is 8 pi, right? So I have I 8 pi by 3, and let me shift the equal to sign further back. So I have e, and then like this. Right. Now again, I can simplify this a bit more because it's more than 2 pi, right? So I can have the answer a little bit. I can simplify it a bit more. So what I'll do is I'll write 2 square root of 2 upon 16 e raised to the power I. So I'll subtract this. I'll subtract 2 pi from 8 pi by 3, and I'll have 2 pi by 3. And this is my final answer, right? I can keep it as this because the question initially was never in Cartesian, right? So I'll keep it, in polar form or Euler form. Doesn't really matter because I can interchange them. I can interchange between them quite instantly, right? Again, if you want to evaluate this, you can write this in polar form. So you'll have cosine of 2 pi by 3 plus I sine of 2 pi by 3. Cosine of 2 pi by 3 is minus half. Sine of 2 pi by 3 is square root of 3 by 2. You can distribute square root of 2 by 16 in both terms, and you'll get your Cartesian form as well. So again, I guess the most difficult part in this question was probably being able to convert from cosine of theta to sine theta. Right? You should remember that. Again, if you have studied trigonometry, I don't think it should be much of a problem. And the second part was here. We've always dealt with basically proper complex numbers, right? Like cosine of theta plus I sine of theta. So here, what was different was the fact that we're taking the conjugate here, right? Because it was minus theta, right? Again, minus theta right here, something like that. So that was a little different in this case. Again, see, if you're still not sure, I can explain this again. It's not an issue. Basically, cosine of theta is cosine of minus theta is cosine of theta because it's an even function, right? So this would be cosine cosine pi by 3 minus I sine pi by 3 because the minus sign would come out. So basically, we'd have x minus iy form, which is generally the conjugate, which we usually talk about, right? So that was the purpose of bringing the minus sign in, right? So now I just had minus pi by 3. What I could have done was I could have put minus pi by 3 here, then I could have added 2 pi. So I would have had cosine of pi by 6 plus I sine of pi by 6, right? Instead of working with pi by 3. And then this part would be a little bigger. So I would have had pi plus some big number here. I think I would have had 25 pi by 3 here instead of 5 pi by 3. And then I would have had to subtract multiple times by 2 pi in order to get to this simplified form, right? So again, yeah, you can look at this question again. It's slightly different, but it shouldn't be that difficult if your trigonometry is pretty strong. So now let's look at a few more examples, especially with complex roots. So we have z raised to the power 4 is equal to minus 8 plus I 8 root 3. So basically we have to find all values of z, right? Again, if you remember, if you don't remember, I'll just rewrite the formula for DeMoivre's theorem for the complex roots, right? So it's basically uh, z raised to the power 1 by n is equal to r raised to the power 1 by n cosine of theta plus 2k pi upon n plus I sine of theta plus 2k pi upon n. I'm going to write it in polar form just because we will have to get the values of the roots again in Cartesian. So polar form is just one step ahead of Euler's form. So now if we have to find different roots, how do we find the value of z? So we would basically do raise the entire thing to the power minus 4. So we'd have z raised to the power 8 minus 8 plus I times 8 root 3 raised to the power 1 by 4. Right? So now we have to find this. So what we do is we first convert this part into polar form, right? So we convert this part to polar form or Euler form, doesn't matter. Convert to polar or Euler form, right? This is the first step you want to do. So first step. So let's go ahead and do that, right? We have minus 8 plus 8 root 3, right? So we have to find the modulus, right? So modulus of z is basically the r, right? So it is square root of minus 8 whole squared plus 8 root 3 whole squared. So it's basically 64 plus 64 times 3. So I can write this as 64 times 4, this, and I'll have 8 times 2, which is 16. Right? That is my modulus. Now, time to find my argument. Again, let's draw it on a plane really quickly so we don't mess up the angles. So we have minus 8, so minus 8 somewhere here, and then we have 8 root 3, so it's somewhere here, like this. So 8 root 3 and 8. So this angle, I can find this angle, and then I can just do, so theta would be pi minus alpha, right? So this would be pi by 3 because it's tan inverse of root 3. So I'm not going to write them. I'm not going to write every single step now. You can figure that out all on your own now. So my theta will be 2 pi by 3. Okay? So that's my theta. So now I have basically converted this form. So I'm going to rewrite the entire thing. I'm going to write it in yellow again. So I'll write all in yellow. So what I'll write is basically I have to find 16 e raised to power I into 2 pi by 3 raised to power 1 by 4. That's what I have to find. Now if I write this in polar form, what I have is 16 raised to power 1 by 4 times cosine of 2 pi by 3 plus I sine 2 pi by 3 raised to power 1 by 4. So let's go ahead and do that now. Here, this is the most important part of the entire process. So first I'm going to simplify this. Obviously I'm going to simplify this. I'm going to keep it as 2. I know this is 2, right? So I'm just going to keep it here. I'm not going to write 2 every time. I'm just going to be wasting my time doing that. So now here's the key part. Now we have to know what n and k is here. So I know, so by this entire standard process, right, 1 upon n. So n has to be 4. So I know n is 4. That means k can take values of 0, 1, 2, and 3, right? Because k is n minus 1. So now let's go ahead and evaluate for k is equal to 0. So for k is equal to 0, right? So what we have here is we'll have cosine of 2 pi by 3, right? Plus 2k pi. So 2k is 0, pi all upon n, which is 4. Right, this, like this, right? Plus I sine, I'm going to write the exact same thing here. 2 pi by 3 plus 0 upon 4, because anything multiplied by 0 is 0, right? Simplify this down. We have 2 pi by 3 upon 4. So 2 pi by 3 upon 4. So I can simplify this like this. So I'll have cosine of pi by 6 plus I sine pi by 6, like this, right? Now I'm going to bring the 2 back, right? So it's basically 2 times cosine of pi by 6 plus I sine pi by 6, like this, right? Now I can evaluate this. I know cosine of pi by 6 is square root of 3 by 2, so I'm going to have square root of 3 plus I left with here. That's my one root. So I can write this as z1, like this. Right, now we do for k is equal to 1. Right, so for k is equal to 1, we're going to do the same process. So cosine of 2 pi by 3 plus 2 times 1 times pi now, right? Because k is 1, all upon n. N remains as it is every time. So sine 2 pi by 3 plus 2 pi upon 4. Again, if you want, if this isn't if it's in paper too, you can use your calculator. If it's not, just get in the habit of working, doing mental math, right? So 2 pi by 3 plus 2 pi. So 2 pi by 3 plus 6 pi by 3, which is 8 pi by 3. So 8 pi by 3 upon 4 plus I sine of 8 pi by 3 upon 4, right? Again, I can simplify this. So I can write this as 2 pi by 3. So cosine of 2 pi by 3 plus I sine 2 pi by 3, like this. Okay. One more thing I forgot to mention is, in this case it worked out, right? I didn't mention it, but always you have to remember. I'll just make a small note of it here, right here, that uh, the value of theta is from pi to minus pi, right? Here it happened, and I noticed that, but I forgot to mention it. But there can be a possibility that angle will maybe come here, right, or somewhere here. The complex number can also be somewhere here. In this case, you have to be sure you take the range of theta to be from minus pi to pi, and you don't add pi to this, right? You don't go beyond pi when you're finding the original argument. Just be sure of it. Just keep in mind, right? I made a note of it here, but in this case, it worked out really well. So you probably didn't notice it, but complex numbers, they oftentimes the examiner will ask you complex numbers from third and fourth quadrant, just so you know, whether theta falls in the range of minus pi and pi. Because if you don't, you will take maybe like 2 pi by 3 or 4 pi by 3, and then you'll get the entire question will be wrong. So just be careful of it. All right, so now let's continue with this. Right, so I'll have 2 pi by 3, right? So 2 pi by 3 is pi minus pi by 3, so it's kind of negative, right? It's not kind of negative, it is negative. So this will be 2 times minus half plus I times square root of 3 by 2. So it will be minus 1 plus I root 3. So that is my second root. So z2, 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 right? That is my second root. Now my third root, right, for k is equal to 2. So I'll have, again, cosine of 2 pi by 3 plus 2 times 2 pi all upon 4 plus I sine 2 pi by 3 plus 4 pi upon 4. So 2 pi by 3 plus 4 pi, right? Let's do it quickly here. 2 pi by 3 plus 4 pi. So I'm going to write it as 12 pi by 3, right? I'm going to have 14 pi by 3 upon 4. So I'm going to have 14 pi by 12. I can reduce this as 7 pi by 6. So I'm going to have cosine of 7 pi by 6 plus I sine 7 pi by 6, like this. Right, now just remember, this value is more than pi. That's okay. I'm only talking about the principal argument right here. The principal argument has to be between minus pi and pi. The rest of the arguments, right? So principal argument also means k is equal to 0, right? That's what it also means. So as long as the principal argument is between minus pi and pi, that's perfectly fine. Okay, so let's evaluate the 7 pi by 6. So that'll be just on the third quadrant. So it would be minus square root of 3 by 2 plus I. And this would also be negative because it's in third quadrant. Cosine and sine are both negative. So minus half. And this was multiplied by 2. So we'll have minus square root of 3 minus I. This. Finally, we are going to have the fourth root for k is equal to 3. Yeah, for k is equal to 3. So for k is equal to 3. So we're going to have cosine of 2 pi by 3 plus 2 times 3 times pi all upon 4 plus I sine 2 pi by 3 plus 2 times 3 times pi all upon 4. So now, if I value this again, 2 pi by 3 plus 6 pi. So 6 pi, I can write this as 18 pi by 3. 18 pi by 3 upon 4. This would be 20 pi by 3 times 4, basically. So it would be 5 pi by 3. So I'll have cosine of 5 pi by 3 plus I sine 5 pi by 3. Again, 5 pi by 3, I often forget what it is. So I'm just going to write this as cosine of minus pi by 3 plus minus I sine pi by 3. Right? So what I did was I just subtracted 2 pi from both arguments. I can do that because I'm going to get to the same place, right? So sine pi by 3 is obviously square root of 3 by 2. Cosine of minus theta is cosine of theta, so I can just write half. Again, multiplied by 2, and I'm going to have 1 minus I root 3. Right? This is my Z4. Z4. Right? Now I'll write it here as well, since I didn't. Z3. Z3. Now, if you plot all of these, now the best way to check them, right? The best way to check whether you've done them right is obviously you can take them in a calculator, and then raise each z to the power 4. So if you raise it to the power 4, you should get minus 8 plus 8 I root 3. The calculator will do it for you. Now, one more interesting property that I want to show to you is that when you plot every single root, right? So square root of 3 plus I, minus 1 plus I root 3, minus root 3 minus I, and 1 minus I root 3. What happens is, right, I'm going to arbitrarily plot this right now. I'm not going to, count everything and then plot it. I'm just going to arbitrarily do it. So this, right, what happens is when you plot them, right, maybe you'll get something like this. So when you arbitrarily plot them, right, what you're going to get is an actual square, right? I know this doesn't look exactly like a square, but when you plot them, right, it will make a square, like a proper square with right angles, and all this, the distance between every single root will be the same. So this is maybe z1, this is z2, this is z3, this is z4, right? It'll happen every single time. So, and what will happen is basically from the origin, you can basically inscribe a circle like this. Sorry, you can, yeah, basically you can make a circle around, right? And the modulus of every point, it'll be the same. So this will be the same, and this will be actually be the radius of your circle. So it'll be like this. The radius will be like this. The shape would be inscribed. The square would essentially be inscribed in the circle, right? Like this, like this. So it remains true for every single. So in this case, we had raised to the power of 4. So here n was 4, right? Here n was 4, and k is 0, 1, 2, 3, right? N was 4 and k was, so even if it was n is equal to 5, then you would have a pentagon. N was at 6, you would have a hexagon. N was a 7, you would have a heptagon, and so on and so forth. And in the end, they would make a circle like this on the plane, right? So this is also, sometimes they might ask you to plot this, and they would all be distributed evenly, right? All the points will be distributed evenly all across the argand plane, right? So yeah, this was a very standard question, and you will get a question like this in your IB paper, right? Maybe it might be raised to power 1/4, maybe raised to power 1/5. I'm not sure, and they might change up the values here and there. So yeah, in the next video, what I'm going to do is I'll take loads of different questions of just powers of complex roots, so you can see the application of Euler's form, polar form, converting between Cartesian and polar form, and using DeMoivre's theorem more often. Okay, so next video I'll make a special video just where I do like loads of different questions, at least 7 to 8 questions, so you get a good grip of what roots of complex numbers and DeMoivre's theorem looks like in play. All right, so this was all for today's video, and I'll see you in the next one.